Okay, so Goldbach's conjecture is simply the idea that if you pick any even number greater than 2, there's some way to add two prime numbers together and get that number. Here's a formal statement of the idea. It simply says that for all n, where n is an integer greater than 2, and really this should say greater than or equal to 2, we can double it and it'll be equal to the ith and jth prime, where I and j are elements of the set of positive integers. Goldbach was a contemporary of Leonhard Euler, so you can see that he actually wrote the conjecture in a letter to Euler in 1742. And in all this time, it has never been proven. It's only been tested all the way up to 4 times 10 to the 18th power. And it has always held up. Obviously, it's been around for hundreds of years. We're not going to prove it today. But we can test it. So what we're going to do is we're going to create some numbers. If we want integers greater than 2, or greater than or equal to 2, we can simply add 2 to this series. And then to double it, we can simply say that. Also in J, you can say that is the double primitive. And you can see these are the even numbers greater than 2. Now to get some prime numbers, again we start with I10, the first 10 non-negative integers, and we're going to add this p colon prefix. So now we have the first 10 prime numbers. We want an addition table of the prime numbers. And in fact, if we want, we can put the word table in here, and that gives us a nicely formatted table. Now if you study this table carefully, you'll see that it contains all the even numbers between 4 and 42. And it also contains a few extra ones that are higher than that, but it's missing 44 and 50 and so on. So it's not complete. But there's no reason that we should be checking a table manually when we have a computer here that can check it for us. So we can use the word E to test whether a particular number is in a set. You can think of it as asking whether the number is an element of the array. And in fact, you can actually say if the elements of this array are elements of this array here. And these two are. If we say 8, then we're going to get a 0 in there, because this 8 does not appear over here. And if we add an 8 to that list, we'll get 3 1s. So now let's get our list of even numbers back. We had 2 times 2 plus I10, and we want to test manually that they're in this list. And in fact, we're going to go ahead and say 20, because that gets us up to number 42. Let's give this a name. We're going to call it evens. Could have done that better. And now if we type evens, we get the values. And let's call this, how about p sums, or sum of primes? What we want to say now is evens is an element of p sums, and test whether that's true or not. And it's going to give us a 0, and that has to do with the rank of this thing. So you can see that p sums is a two-dimensional array. In J, you would say it's a rank 2 array. Basic question 0 is the rank at which this verb, E, operates. The answer says that it operates at rank infinity, meaning it's going to operate on the outermost rank of its arguments. The first infinity here is saying what happens when you say E 1, 2, 3 or something like that, where there's no left argument. It has a completely different meaning than you give it 2 arguments. Well, let's say that we have I33, which is this. Now, the array as a whole contains items, which are rows. So this is an array of 3 arrays, 0, 1, 2, and 3, 4, 5, and 6, 7, 8. And if we say 3, 4, 5, E, I, 3, 3, it's going to say 1 because that row exists in the array. But if I just want to know if the number 3 exists in here, oops, 3, E, I, 3, 3, it's going to say 0 because this is not an item in this. It's not an element of this. To change that, we can do one of two things. First, we can take this and we can add a ravel in front of it, which is a comma. And the word ravel comes from the idea when you're knitting like a sweater and you pull the string and the sweater will unravel. Ravel and unravel mean the same thing. Anyway, this gives you the verbs. And so this gives you a flattened... Anyway, raveling gives you the content of the array without the structure. It reduces it to a single dimension or a vector. So it reduces it to a rank 1 array, which you might call a vector in some other language, or a list. So that's one way to do it. And so now we can say, is 3 an element of the ravel of I33? And the answer is yes. What about 3? Well, we say 3, 4, 5 again, we get 1, 1, 1. What about 3, 9, 5? Well, the 9 isn't there. Okay, so to recap, we have evens, and we have p-sums, and we're going to ravel p-sums, and we're going to ask, for each item in evens, is it an element of the ravel of p-sums? So this is returning a set of bits, or an array of bits, 1 bit for every item in evens. So if we say, what's the length of evens? It's 20 items. What's the length of this number, or this array? And we get 20 items. Now we can say, what is the sum of all those ones? And we get 20. So we can say, does the sum equal the length? And then that should say 1. But there's a much better way to do that, and which is to take the AND operator, which is that, and insert the AND operator in between all the items. So when you say 1, 0, 1, and you add them together, this is as if you were saying 1 plus 0 plus 1. And if you say AND instead of add, it's as if you're saying 1 and 0 and 1, which is 0. Because 0 means false, and when you AND false with something, you always get 0. If they're all true, you get 1. Now, it doesn't matter how many things you have. If there's any 0 in there, you're going to get a 0. So basically, you could pronounce this word as all. And we could then say all evens are elements of the ravel of p-sum. Oops. And that should say 1. I prefer to just write it this. I know this is more readable if you're not used to J, but once you get used to it, it's perfectly obvious what this means, and it just seems easy. It just seems cleaner once you know the notation. Just as if you had to say 2 plus 2 to get 4. Well, you could say plus equals, and then this works. So yeah, this then is testing. Well, let's see. Let's get it here. This is testing that all the evens are elements of p-sums, elements of the ravel of p-sums. So as it stands now, if we ask for the type of evens and the type of p-sums, we're going to see that they're both nouns. But this only gives us the chance to test for the 20 numbers in evens, for these 20 numbers. And what I'd like to do is parameterize this. So let's redefine evens. Right now we've defined evens as, this is a test. I'm going to test this. I'm going to test the following assertion. I'm going to say that evens matches 2 times 2 plus I-20. And it should say 1, that they match. If I say equal, I get that. And if I said that, I should get 1. And that is what, it's very similar. It's not exactly, but it's the idea is similar to what this operation does, this verb. So 2 times 2 plus I-20 should match evens, and it does. And so now let's just redefine it. But instead of saying I-20, I'm going to say that there's some y, and rather than make it 20, let's make it 10. And then we're going to say 2 times y. And we're going to say that this matches as well. It does. And since it matches, let's do that. And then we're going to remove this part, quote the whole thing, and then I'm going to say it's a verb. And so now if I say evens 10, I get that. If I say evens 20, I should see even more numbers. And if I say evens 5, I should get 10 numbers. And we can test that by saying, what is the length of that list? It's 10. And you can see that this is the same as this. So now, if I ask for this, the type of evens and p-sums, I'm going to get a verb and a noun. But I want to do the same thing I just did for p-sums. And when we defined p-sums, the sum of primes, we said it was, let's test this again, it's the sum, the table, it's the addition table, or the sum table, of the primes I-10. There we go. And again, we already said that y equals 10. So I'm just going to say IY. And again, I'm going to make it a verb. Whoops, I've made a mistake here, because now I'm not assigning it, I'm checking it. And when you check for the verb, it's doing some weird things here. I'm actually just going to redefine it. And now we get a verb and a verb. And p-sums of 10 should give us that. Now notice that I didn't define what y is, but y is not this y. I can say erase y, and then what is y? We don't know. And yet p-sums 10 is still going to work. And p-sums 5 is going to give us a smaller item, and p-sums 15 will give us a bigger one. And the reason for that is that whenever you say verb y, you're defining a verb, and y is simply the name of the right argument. So 1, 2, 3, 4 is going to give us that. We can actually be more specific. It's not just a verb, it's a monad. A monad is simply a verb that has one argument on the right hand side. 1, 2, 3, 4. It's going to give us that. The argument here is an array. An array and a scalar, it doesn't matter, it's just that it's the argument on the right hand side. And if we say dyad, then now it's going to require 2 arguments. And if I press enter here, it's going to complain about it. Domain error, because I've said it's a dyad, but I only gave it 1 argument. And so now if I say A, B, C, D, E, F, G, I could type, it's going to give me that. And if I say Y here, it's going to give me that. So that's what a dyad is. Okay, so now I want p-sums, p-sums should be a dyad be a monad, and I want it to have the following definition. I want it to be the ravel of the table of sums of the primes for the right argument. And if I say p sums 10, I should get the list. This is showing the raveled items. If we want to show the whole thing, we can reshape it again back to 1010 and we get the original list. But I just incorporated the comma because that way we don't have to use it here. We can just say evens element of p sums again. But now this is going to be, remember these are both verbs now, so we have three verbs together. So what happens here is now this is a verb, and we can take that verb and put parentheses around it, and we can call 10, and we get our original list of numbers. And this is called a fork. You can see that this expression right here has three verbs in it. It has the verb evens, which we've defined here, e, which is a primitive, and p sums, which we've defined up here. And when we do this, what's happening is this number is being fed into this, and then the results are being fed into this. So it's as if we're saying evens 10, which gives us this, element of p sums 10, or are these elements in p sums 10, and we get this. And so what we're doing is we're factoring out that 10 and then putting these together, and J does this for us. It's just part of the syntax of J. It's called a fork. Okay, so now we have evens and we have p sums, and now to make the Goldbach conjecture we want to say Goldbach equals, and we could say three, we could say verb. I have a tendency to type 3 and then go back later and clean it up for readability. So I'm going to do that here. We could say this. We could say we want all of the numbers in evens e p sums y to be 1. So Goldbach 10 test the first 20 numbers. Or the first 20 even numbers, and there we go. But I don't like that, because it's just easier, now that we've specified things this way, to just specify this as a tacit verb. Tacit meaning we don't mention the y argument at all, we just say that. That all evens are in p sums. And then Goldbach 20. Now we can test 200, which, okay, so now we have evens and we have p sums defined, and these are actually all we need to test the Goldbach conjecture up to an arbitrarily large number, the limit of our memory. For example, if we want to test the first 2,000 numbers, or the first 2,000 even numbers greater than 2, we just say evens, same thing we've been doing this whole time, evens are element of p sums 2,000, and we get a bunch of 1s. And since that's too many to see, it's actually hopefully 4,000, it is, we can just use our little all trick and we get 1. So they are all sums of 2 prime numbers. Now, I don't know about you, but I'm not terribly satisfied with that. We can just take this on faith that it's working. But it would be nice if we could actually look and see what the prime numbers are that are being added together. And so very quickly, I'm going to show you how to do that. When you say p sums 20, actually we're going to do 5. The length of this is 25. It's obviously a 5 by 5 table that has been unraveled. Whenever you have a grid like this, you can take the width of the grid, and which is going to be 5 here, and you can divide any particular number, if you have I55, you're going to have, you can take the index of a position here, which is what we're, you can take the index of any particular square. So for example, let's say 23, and we're gonna divide this by 5, and then we're going to take the floor, and this is going to tell us it's telling us which row the number 23 is going to be in. 0, 1, 2, 3, 4. And then if we take 23 and we take the remainder when we divide by 5, whoops, in J you say it the other way around. You say 3. So 0, 1, 2, 3. And you can see that at the coordinates 4, 3, you're going to have 23. And what we can do here now is we can say, we can make a little fork that does exactly this. We can compose the floor. I'm going to go ahead and just use the reverse of division. I'm going to flip the order on this one rather than this one, and then compose it with the remainder or the residue. And actually, if you put a dot here, you're going to get a slightly different shape. I'll go ahead and show you what it looks like without. And I'm going to call this div mod. Div mod out of. It's the traditional name for this operation. And although the parameters are slightly backwards from what you might be used to. So I25, we now have this, and what I wanted was to see them in pairs, and adding this dot here allows me to do that. And you can see that these are really just counting up to 25, 0 to 24 in base 5. So another way we can do that is say I25 55 base. Same thing. And in fact, that's another way to do that. So now, we can take these, we can box them. Oops. But let's box the individual items. And the parentheses are to separate that 1 from the 5 and the 5, otherwise it would be an argument to the base or anti-base, whatever that is. And then we're going to take this and then we're going to reshape it back to 5, 5 here. And so you can see that when you oops, you can see that this table corresponds to the positions in here. And so simply by using this phrase or our div mod, we can use either one. In fact, I'll prove it to you here. 5 div mod I25, you get the same thing. And what that's telling you is the coordinates. It gives us a way to map these numbers to these coordinates. 5 div mod I55. You can see it's well, it's it's a mess to see this, but you can say each. Oops. There you go, and that's also the same thing. So what we're going to do, so what I want to do with this now is I want to take I want to go back to p sums, and previously we had said evens e p sums, right, for however many numbers. Ooh, and we have a 0. Okay, and so the 0 here, we can actually explore this in a minute. The 0 here is just because I chose to double the number, and it looks like we just don't have enough primes. Remember we said in evens that we're taking 2 times y, and if we just take this number back down to y, so that the number of primes and the number of evens are the same, then the number of primes should be more than ample to cover that. So now we're only looking at 5 numbers. But we can also say p sums 5, and 5, 5, reshape p sums 5, and it looks like evens 10 would have been 22, which is there. Oh, but 20 is not there. So the next to the last one, the one in the 20 slot, is not in this table yet. And so we needed actually probably p sums 6. I bet if it's 6, 6, reshape p sum 6, then finally it shows up. So we just didn't have enough primes. And by setting it back to 1, the fifth prime number, which is p5, is 13, which is much higher than 2 times 5, simply because primes are rare and even numbers are common, so the primes are going to be much larger, and therefore you're almost certain to have enough coverage here. So anyway, to go back to what I was saying, we were doing this before, but another thing we can do, instead of e, we can use a verb called I, and the order for what we want to do is actually going to be in the opposite order. Evens, so we're going to switch them around. I could have said I and then put the tilde there to swap them, but it doesn't matter. Either way, and so you can see so annoying. So either way, either way works. Anyway, you can see that what these are, what this is telling you, it's the index of these even numbers in p sums. Just to give you a simpler example, if we say hello, what is the index of the e? It's at index 1. What's the index of the h? It's at index 0. And likewise, we're just doing the same thing here. So p sums 5 is this, and you can see that the first, maybe we should have called this Goldbach number, but the evens 5 is going to be 4. So you can see this is in that slot. P sums 5. 6 is up here in the 6th slot. We can say this, and we can join it with this. Whoops. Because that would be a square number. So we're going to square the argument here and get that, and bring this back over here. So this column here is is I of the square. This number right here, the symbol asterisk and the colon squares this number. That's weird. And actually we can do this to get a little more compact number, compact representation. So again, so this column, or this row now, is the index. You can see these are just in sequential order, and here are the values in the table. And we know how to map the index to the position in the table. So what we can do now with this is that we're going to take, well, let's look at the table again, just to remind ourselves of how this table works. In fact, let's look at it like this: p sums. We're taking this table, and I'm going to put the word table in there again, and then I5. And so the idea is that this is the this is prime number 0, P0, P1, and so on. So by taking, if we can find the coordinates of a number in this table, right, which we know how to do because we used the divmod trick or the base 5 trick, and so now we have the column and the row, and that tells us which prime numbers were added together to get this value. So for 10, well, let's do 14. Well, let's do 12. So let's do 12. The width of the table is 5, so 12 or 5 div mod 12 is going to give us 2, 2. So 0, 1, 2, 0, 1, 2, and we come across and we get to 12. Okay, well, we got a bug. No, we don't. We do not have a bug. All right. Okay, so now let's look at the position of this 12 here. So p sums 5, and then we're going to say what is the, I guess I want that backwards. So I want position 13. So I5, 13 is here, and let's actually just do it like this. If you want to, this is just a trick for showing how how to visualize a matrix here. There's actually some visualization tools, but I'm not going to show them off right now. They're not actually working for some reason. So 13 equals that, and you can see that the 1 is right there. And so, you know, it's 2 over and 2 down, so it's right here. So the index of 12 is 13. This is slot 13 here. And if we say 13, we just saw this trick a minute ago. If we say 5, 5, 13, we get 2, 3. And what this means is it's 0, 1, 2, 0, 1, 2, 3. So position index 13 has the value 12 here, and it's at coordinates 2, 3 within this table. In fact, let's do this again. We'll take this out, and if we say 2, 3, and we extract that, we want to box this number, then we get the value 12. If we want the number right underneath that, we would say 3, 3. Just the way computers work, the the y value comes first, the y coordinate comes first. And we get 14, which is the number right underneath. And if we wanted the one for the left, we would have said 2, 2, which is 10. So that's how this is the extraction value, or the extraction verb. So, now that we have this, what we can do is we can say p sums evens, so the index of the evens in the p sums for the first 5 numbers, and then we're going to say 5 div mod that, take that index, div mod by 5, and then we now have these row and column numbers. These are the rows and these are the columns, where the y value is on the left here and the x value is on the right. And now we can map those back to the primes. So and then let's just we could make a fork out of this or something, but I'm not going to worry about it. P sums 5, and then we're going to add those on there, and I didn't do it right. Still didn't do it right. I never remember these things, and I have to try them out a couple times. I'm actually just going to whoops, what I wanted to say was okay, so now we can actually say, if we wanted to, we could actually put evens 5 and just kind of put that next to it. So what this is telling us now is that the number 4 is the sum of 2 and 2, which are prime numbers. 6 is the sum of 3 and 3. 8 is the sum of 3 and 5. 10 is the sum of 3 and 7. And 12 is the sum of 5 and 7. So this is actually telling us what these values are. And then I'm just going to go ahead and make this into a function too. Again, we'll say y, put y here, and obviously a lot of people like to play okay, so now let's just actually go ahead and turn this into a function. And this is not going to be like the most elegant function because I'm just kind of cobbling it together from whatever's in front of me. But it's a monad. And we're going to do that. And we want by. And then we can pass this here, and now we've got a verb. There we go, still defined. And then let's call this Goldbach. So now we can take the first 20 Goldbach numbers. Let me get this. we take the first 200 Goldbach numbers, and we get a big long thing like this. And we can verify that 402 is an even number, and the 397 is a prime number, and 5 is a prime number, and you add those two together and you get 402. And then I'm going to try this now. Very likely, and of course at this point we can just start seeing how much of how many of these numbers can we calculate as big as we want. But I'm not going to do that because when I tried it a little while ago, the video recording software is taking up a lot of RAM, and it just slowed my computer to a crawl. And it could be that this algorithm is just not very good. But let's say that we want to take 200 and we want to get the 35th Goldbach number, which should be 37 times 2, I would think. We'll see. 74, 37 times 2. Woohoo! Yeah, so, and there it is. 71 is a prime number, 3 is a prime number. You add them together, you get 74. And so that is our test of the Goldbach number. Here it is. Again, we could clean it up considerably, but it's done the job, and this is kind of and it kind of but it's done the job. And that's kind of the nice thing about J, is that you can work out some really complicated stuff at the prompt here without really having to write a standalone program. And so that's kind of the good and bad thing about J, is that you're able to write really complicated stuff just at the prompt here without opening up a text editor or anything like that and saving your work. And it's easy to cobble together some rather long chains of text and code, and hopefully this is a little bit hopefully this code isn't too cryptic, but you never know. So just for reference, here is evens, here is div mod. I'm just going by the order, I'm just going across here. Here's psums, and evens again. So that is the complete code to our Goldbach verb, and the results are the first 200 Goldbach numbers in 3 columns with the Goldbach number and then the 2 primes that are summed to get that number.